Science's biggest leaps often start with a simple accident. 27 experiments, stumbled upon by chance, peeled back the layers of our perceived reality to reveal a hidden architecture governing everything from the smallest particles to the vast cosmos. By the end of this journey, you will see how these unplanned discoveries point to a single, interconnected structure of reality. We will uncover how a failed attempt to detect a cosmic medium rewrote physics, and why fogged photographic plates hinted at invisible forces within the atom. What does it mean for our understanding when the universe's deepest truths are found not by design, but by accident? Alexander Fleming returned to his messy laboratory after a vacation, only to find something strange growing on his Petri dishes. A common mold had contaminated his bacterial cultures, but instead of ruining the experiment, it had created a clear, bacteria-free circle around itself. That chance observation led directly to penicillin, a discovery that would save millions of lives. This was not the result of a meticulous plan. It was a fortunate accident, a moment of serendipity where a prepared mind recognized the significance of an unexpected event. This pattern repeats throughout the history of science. The greatest leaps forward often arrive not from a straight path of inquiry, but from a sudden, unplanned turn. This is the heart of scientific serendipity. It is not mere luck. It is what happens when rigorous experimentation and deep knowledge collide with a surprising result. For centuries, the scientific method was portrayed as a rigid sequence, a linear march from hypothesis to experiment to conclusion. But the real story is far more chaotic and fascinating. The most profound discoveries frequently begin as anomalies, as little glitches in the data that do not fit the established model. Philosopher Thomas Kuhn described these moments as the catalysts for scientific revolutions. When enough of these puzzling anomalies accumulate, they can shatter an existing paradigm, the entire framework of how we understand the world. This forces a fundamental shift, a revolution in thought that eventually leads to a new and more accurate paradigm. The old model of a static, predictable universe gave way to the strange realities of quantum mechanics precisely because of such unexpected results. The 27 experiments we will explore are a testament to this process. Each one is a story of an anomaly, a result that did not make sense at the time, a crack in the surface of reality that, when investigated, revealed a deeper, hidden structure beneath. This foundation changes how we view the pursuit of knowledge. It encourages a mindset not of rigid certainty, but of open-ended curiosity. It asks us to pay close attention to the things that go wrong, to the outliers and the mistakes, for they may be the very whispers of a deeper truth waiting to be heard. This brings us directly to our first case, a famous experiment that began with a complete and utter failure, a failure that would ultimately rewrite our understanding of light, space, and time itself. That simple failure to find a stationary ether was a crack in the foundation of classical physics, but another experiment just as elegant would pry that crack wide open. It began with a beam of light and a barrier with two narrow slits. Common sense tells us that tiny particles, shot one by one at this barrier, should pass through one slit or the other and accumulate on a screen behind it as two distinct bands, a simple record of their particle-like paths. This is not what happens. When scientists performed this experiment, a stunning pattern emerged on the screen, not two bands, but a series of many stripes, light and dark, a signature of interference. This is the behavior of a wave, like ripples on a pond, where crests and troughs overlap to create areas of heightened and cancelled-out intensity. The individual particles were somehow interfering with themselves, as if each one passed through both slits simultaneously, a wave spreading out and meeting on the other side. This was the brilliant, accidental discovery of Thomas Young in the early 1800s. The implications became even more bizarre when later versions of the experiment used electrons, the fundamental particles of matter. Even these tiny bits of solid stuff produced a wave-like interference pattern. It seemed that the very act of being unobserved allowed an electron to exist as a spread-out wave of possibilities. But the true mystery deepened when scientists tried to catch the electron in the act. The moment a detector was placed to observe which slit each particle went through, the interference pattern vanished. The electrons now being watched began behaving like proper little particles again, forming only two bands on the screen. It was as if the particle knew it was being looked at. This is the heart of wave-particle duality. An electron is not a particle or a wave. It is something more fundamental that reveals either property depending on how we choose to interact with it. Our measurement forces it to pick a side. The physicist Niels Bohr called this principal complementarity, the idea that seemingly contradictory behaviors can both be true and necessary for a complete description of reality. This single experiment forces us to abandon the comforting idea of a fixed, objective universe. It suggests that at its core, reality is a tapestry of probabilities, not certainties. The solid world we perceive is just a shadow, a single manifestation pulled from a deeper, wave-like structure of potential. How could something so small be so deeply affected by a mere glance? This quantum mystery, born from a simple pattern of light and dark bands, sets the stage for all the strange discoveries that followed. Those dark and light bands from the double-slit experiment hinted at a quantum strangeness, but this next story begins with a question that seemed far more straightforward. What carries a light wave? In the late 19th century, physicists were convinced space was not empty. It had to be filled with an invisible, stationary substance they called the luminiferous ether. This was the medium through which light waves were thought to ripple, much like sound waves need air to travel. Two American scientists, Albert Michelson and Edward Morley, designed an exquisitely sensitive instrument to prove it. Their interferometer aimed to catch the Earth in the act of moving through this cosmic ether wind. The plan was brilliant. They would split a beam of light, sending the two parts on perpendicular journeys before recombining them. If the ether existed, the Earth's motion through it should cause one light beam to travel slightly slower, creating a tiny shift in the interference pattern when the beams came back together. They expected to see a telltale fringe shift, a wobble in the pattern of light that would confirm the ether's presence. The result was a profound nothing. No shift, no wobble. No matter how they oriented their device or when they performed the measurement, the speed of light remained stubbornly, impossibly constant. It did not change with the Earth's direction. This was a monumental failure, a null result that should have been a dead end. Instead, it was a silent bomb that shattered classical physics. The ether did not exist. There was no stationary stage for the universe. This accidental discovery, this failed detection, forced a radical rethinking of the very nature of space and time. It cleared the way for a young patent clerk named Albert Einstein. His theory of special relativity began with this very premise, that the speed of light is a universal constant for all observers, no matter how fast they are moving. From this single fact, the familiar concepts of absolute space and absolute time melted away, revealing a deeper, interwoven fabric called spacetime. A meter stick is not always a meter long. A second does not always last a second. They stretch and compress relative to your motion. Historians see this as a pivotal lesson in the power of a negative result. Michelson and Morley were not trying to destroy a paradigm. They were trying to confirm one. Yet their meticulous failure to find the ether revealed a far more dynamic and strange reality, a continuum where space and time are not a static backdrop but active, relative participants. This principle of relativity would become a cornerstone, a thread we will see connecting to other cosmic revelations that were also discovered by chance. Radiostatic, a low and persistent hiss, was the last thing Arno Penzias and Robert Wilson wanted to hear. Working with a massive horn-shaped antenna in New Jersey, their goal was to map faint radio signals from the edges of our galaxy. But this noise was an unshakable problem, a uniform static that came from every direction in the sky, day and night. They checked everything. They pointed the antenna at New York City, thinking it might be urban interference. They investigated military tests. They even suspected the real culprits were a pair of pigeons nesting in the giant horn, leaving what they diplomatically called a white dielectric material. They meticulously cleaned it all out, but the hiss remained, an unwavering cosmic whisper they could not eliminate. What they dismissed as an annoying defect was, in fact, the most important signal they could ever hope to receive. That static was the faint, cooled remnant of the universe's birth. It was the cosmic microwave background radiation, the afterglow of the Big Bang itself. Billions of years ago, the entire cosmos was an unimaginably hot, dense fireball. As it expanded and cooled, the energy from that initial explosion stretched into the microwave part of the spectrum, creating a thermal imprint that now fills all of space. Penzias and Wilson had accidentally tuned into the echo of creation. Their frustrating noise was the definitive proof that our universe had a specific, fiery beginning. It confirmed a key prediction of the Big Bang theory, providing a snapshot of the universe when it was just a few 100,000 years old. This was not just another data point. It was a window back to the very infancy of everything. The discovery was so profound that cosmologist George Smoot would later describe mapping its tiny variations as like seeing the face of God. This cosmic background radiation revealed a universe that was fundamentally uniform on the largest scales, a smooth canvas upon which galaxies would later form. It solidified our cosmic timeline and gave us a tangible connection to the origin of space and time. How astonishing that the key to understanding the grandest story ever told was hidden not in a complex calculation, but in the mundane frustration of a signal that would not go away. This echo from the dawn of time showed that the universe itself carries a memory of its explosive birth, a memory we can still detect with a sensitive enough ear. While Penzias and Wilson were listening to the ancient whisper of the cosmos, another pair of scientists was aiming for something much smaller. Otto Stern and Walther Gerlach sent a beam of silver atoms through a specially shaped magnetic field. They expected a simple result. According to classical physics, the tiny magnets within these atoms should have been able to tilt at any angle, and the magnetic field would simply smear the beam into a continuous blur. But the apparatus revealed something entirely different. The single beam did not smear, it cleanly split in two. Only two distinct beams emerged, hitting the detector screen in two separate spots. This was not a blur, it was a choice. The atoms, it seemed, could only point in one of two directions, up or down. Nothing in between was allowed. This was the stunning, accidental discovery of quantization in action. A property that was thought to be smooth and continuous like a dimmer switch was actually granular and digital like an on-off switch. The property they had discovered became known as quantum spin. It is a form of intrinsic angular momentum, a kind of tiny rotation that is built into every fundamental particle. But do not picture a little ball actually spinning. This rotation has no classical counterpart. It is a purely quantum mechanical property, a fundamental label that defines how a particle interacts with magnetic fields and with other particles. The Stern-Gerlach experiment had stumbled upon a new layer of reality, a hidden architecture where the options are not infinite but strictly limited. This quantization is everywhere in the microscopic world. Electrons in an atom do not orbit at any distance they please. They exist only on specific, discrete energy levels, like rungs on a ladder you cannot stand between. The entire stability of matter depends on this principle. Without it, atoms would collapse. This single experiment, born from a surprising split beam, revealed that the universe at its most fundamental level is not a smooth continuum but is instead pixelated. It is built from tiny, indivisible packets of energy and properties. How many more of these digital rules are waiting to be found, governing the seemingly analog world we experience every day? The universe's deepest structures often announce themselves through the most mundane of accidents. Henri Becquerel, a French physicist, was working with uranium salts in 1896, fully convinced they needed sunlight to emit their mysterious rays, a phenomenon known as fluorescence. He prepared his experiment by placing the uranium salts on top of carefully wrapped photographic plates, intending to expose them to the sun, but the Parisian weather had other plans. For several days, the skies remained stubbornly overcast. Frustrated, Becquerel stored the entire assembly, the uranium resting directly on the sealed plates, away in a dark drawer. When he finally developed the plates out of sheer curiosity, expecting to find nothing at all, he was met with a stunning sight. The plates were heavily fogged, as if they had been exposed to a powerful light. The uranium had been emitting its penetrating rays completely on its own, without any need for sunlight. This was the completely serendipitous discovery of radioactivity. He had stumbled upon a hidden energy source locked within the atom itself. The elements were not all stable and eternal. Some were fundamentally unstable, spontaneously decaying and firing off particles and energy from their cores. This invisible, energetic process was happening all the time, all around us, a silent transformation of matter that no one had suspected. Becquerel's fogged plates opened a doorway into the atomic nucleus, revealing a subatomic world teeming with immense, restless power. It showed that the atom was not a solid, indivisible billiard ball, but a complex structure with a dense, energetic heart. This energy, once understood, would lead directly to our comprehension of nuclear forces, the very glue that holds the nucleus together against its own tremendous internal pressure. It was a fundamental revelation that matter itself is dynamic and unstable, capable of profound transformations. This discovery reminds us that the most potent forces shaping our world are often completely invisible to our senses, operating just beneath the surface of perceived reality. Becquerel's chance finding set the stage for a cascade of other subatomic surprises, each one peeling back another layer to expose the raw, energetic engine at the heart of everything. Atomic clocks, the most precise timekeepers ever built, were about to take a trip around the world. In 1971, physicists Joseph Hafele and Richard Keating placed cesium atomic clocks aboard commercial airliners. One jet flew east with the rotation of the Earth, while another flew west against it. After the journeys, the scientists compared the clocks that had flown with identical clocks that had remained stationary on the ground. The results were not a tiny error, they were a direct confirmation of a staggering truth. The clocks that had been in motion were measurably behind. Time itself had passed more slowly for them. This was not a flaw in the clocks, it was a feature of the universe, a phenomenon called time dilation that Einstein's theories had predicted decades earlier. The experiment revealed that time is not a universal metronome ticking at the same rate for everyone. Its flow depends entirely on your state of motion and the strength of the gravitational field you are in. The faster you move, the more time slows down for you relative to a stationary observer. Even the slight difference in gravity between the altitude of a jet and the surface of the Earth creates a tiny but measurable shift. This was relativity in action, not in a thought experiment, but in the real, practical world of Pan Am flights and airport terminals. The implications are profound. A clock on the top floor of a skyscraper will tick very slightly faster than one in the basement because it experiences a minutely weaker gravitational pull. For the astronauts on the International Space Station, moving at thousands of miles per hour, time passes just a bit slower than it does for us on Earth. Over a long mission, they return home having aged a fraction of a second less than everyone else. This experiment peeled back the illusion of a single objective now. It showed that time is a local experience, woven inseparably with the three dimensions of space into a four-dimensional fabric called space-time. Your journey through this fabric, your personal history, is unique to your path. There is no master clock for the cosmos. How can something as fundamental as the passage of time be so personal, so relative? This concrete proof of time dilation suggests that the constants we rely on are not so constant after all, and that our everyday perception of reality is a comfortable simplification of a far more malleable and interconnected structure. A perfect vacuum seems like it should be nothing at all, a true and complete emptiness. But in 1948, a Dutch physicist named Hendrik Casimir predicted something that defied this simple logic. He calculated that if you placed two uncharged, perfectly smooth metal plates incredibly close together in this vacuum, mere nanometers apart, they would be spontaneously pulled toward each other. There was no obvious force at work, no gravity, no magnetism, yet the plates would attract. When this delicate experiment was finally performed, that is exactly what happened. The plates, suspended in nothingness, gently clicked together. This bizarre phenomenon became known as the Casimir Effect. It was a ghostly push from an unseen world. The explanation lies in the nature of empty space itself. According to quantum mechanics, a total vacuum is not empty. It is a seething, bubbling sea of activity. So-called virtual particles are constantly flickering into and out of existence, borrowing energy from the vacuum for an impossibly brief moment before annihilating each other. These are not particles in the ordinary sense, but fleeting fluctuations in underlying quantum fields. This chaotic dance happens everywhere all the time. Now place two plates very close together. The gap between them is so tiny that only certain wavelengths of these virtual fluctuations can fit inside. The wider space outside the plates, however, allows for all possible wavelengths. This creates a pressure difference, with more virtual particles pushing on the outside of the plates than on the inside. The result is a net inward force pushing the plates together. It is like two boats in a choppy harbor being pushed together by the waves outside, while the calmer water between them offers less resistance. This proved that the quantum vacuum has a real, measurable energy, a background hum to the universe known as zero-point energy. The void is not void. It is a vibrant, energetic medium, the lowest possible energy state from which all particles and forces arise. This discovery was a stunning validation of quantum field theory, the idea that what we call particles are merely excited states of these invisible, omnipresent fields. The solidity of matter is an illusion atop a deeper, dynamic structure. The Casimir effect makes you wonder what other invisible pressures are constantly shaping reality, an unseen ocean of energy whose waves we have only just begun to feel. Einstein was deeply troubled by the implications of quantum mechanics. He, along with physicists Boris Podolsky and Nathan Rosen, crafted a brilliant thought experiment in 1935 designed to prove that the theory was incomplete. They argued that if quantum mechanics were a full description of reality, it would lead to something absurd, something they called spooky action at a distance. Their logic was based on a concept we now call entanglement. They imagined a pair of particles that interacted and then flew far apart. According to quantum rules, measuring one particle, say, finding its spin pointing up, would instantly force the other particle, no matter how far away, into the opposite down state. For Einstein, this was impossible. No signal can travel faster than light. This instantaneous connection violated the very principle of locality, the idea that objects are only influenced by their immediate surroundings. He insisted there must be hidden variables, unknown properties set when the particles parted ways that predetermined their outcomes, restoring a sensible, local reality. For decades, this EPR paradox remained a philosophical debate, a thought experiment highlighting a strange quirk in the math. Then, a physicist named John Bell entered the stage. He devised a theorem, a practical way to test whether these hidden variables could exist. He was not trying to prove quantum mechanics right. He was trying to find a concrete way to settle the argument. When experiments were finally built to test Bell's inequalities, the results were not what Einstein would have hoped for. The experiments accidentally confirmed that the spooky action was real. Entangled particles do influence each other instantaneously. Measuring one does indeed set the state of its partner, even if they are on opposite sides of the galaxy. This was the shocking discovery of non-locality. The universe, at its most fundamental level, is not a collection of separate, independent objects. It is a deeply interconnected web where space is not a barrier to connection. This quantum link does not allow for sending information faster than light, preserving causality in a cosmic sense, but it does shatter our classical intuition. How can two things be so intimately linked that they function as a single system, regardless of the vast emptiness between them? This forces a profound reconsideration of what it means to be separate. Entanglement suggests that the independence of particles is an illusion, that reality is fundamentally holistic. As we continue, we will see this theme of hidden connection weaving through other accidental discoveries, revealing a cosmos far more unified than it appears. Einstein's spooky connections revealed a universe woven together, but what about the stuff it is made of? For centuries, the proton was considered a fundamental, solid dot, a single point of positive charge. That simple picture shattered in the 1960s when physicists Jerome Friedman, Henry Kendall, and Richard Taylor aimed a powerful beam of electrons at a target of protons. They expected the high-energy electrons to bounce off the protons in predictable ways, as if pinging a smooth, featureless sphere. The results were anything but predictable. The electrons scattered wildly, rebounding at large angles as if they had struck something incredibly small and hard inside the proton itself. It was like firing a bullet at a soft pillow and having it ricochet as if it had hit a piece of solid steel buried deep within. This was the accidental discovery of deep inelastic scattering, and it revealed that the proton was not fundamental at all. It was a bag of smaller, point-like particles. These internal objects were soon identified as quarks, the building blocks of protons and neutrons. This was a monumental shift. The solid, stable nucleus of every atom was suddenly a seething crowd of more fundamental entities. The quark model explained the baffling results. Quarks carry fractional electric charges, a concept that was once thought impossible. A proton is made of two up quarks, each with a charge of positive 2/3, and one down quark with a charge of negative 1/3, adding up to the familiar positive 1 charge we knew. But this raised a new puzzle. If quarks are trapped inside protons, what force is so powerful that it can imprison them forever? The answer is the strong nuclear force, the most powerful force in nature over short distances. It is mediated by particles called gluons, which act like a relentless glue. As you try to pull quarks apart, the energy in the gluon field between them increases so dramatically that it becomes more energetically favorable to create new quark pairs from the vacuum rather than to allow a single quark to exist in isolation. This is quark confinement. You can never have a lone quark. They only exist in groups, forever bound within the particles that make up our world. This accidental discovery peeled back another layer of the cosmic onion, showing that the solidity of matter is an emergent illusion from a deeper, frantic dance of confined charges and unimaginably powerful forces. It hints at a universal symmetry governing these interactions, a hidden mathematical beauty dictating how reality assembles itself at the smallest scales. How many more layers remain, and what other secrets are waiting to be set free by another fortunate mistake? Gravity is supposed to pull on matter, but what about pure light? In a tower at Harvard University in 1959, physicists Robert Pound and Glenn Ribka aimed to find out. They fired a beam of gamma rays from the top of the building down to a detector in the basement. According to Einstein's general relativity, gravity is not just a force but a curvature of spacetime itself. Light, having energy, must climb out of this gravitational well. As it struggles against gravity, the light should lose a tiny amount of energy, and since a light wave's energy is tied to its frequency, this loss would cause its color to shift very slightly toward the red end of the spectrum. This is gravitational redshift. The effect Pound and Ribka were looking for was incredibly small, a change of just a few parts in 1,000 trillion. They expected to see it, but the sheer precision of their accidental confirmation was what stunned the scientific world. Their apparatus, meticulously designed to test the theory, ended up providing one of the first and most direct proofs that gravity does not discriminate. It bends the path of light and saps its energy just as it pulls on a falling apple. This revealed a profound link between energy and the shape of the cosmos. The experiment showed that gravity affects everything that carries energy, weaving matter and light into the same cosmic fabric. It demonstrated the universality of relativity in a new, tangible way. If light, the fastest thing in the universe, must pay a tax in energy to escape a gravitational field, then the connection between energy and space-time curvature is absolute. This subtle redshift is a whisper from the fabric of the cosmos, a reminder that the stage itself is dynamic and interactive. How many other invisible interactions are constantly reshaping the light and energy that flows through the universe? Energy was vanishing. Inside a cloud chamber, scientists watched the trails of beta decay, where an unstable atomic nucleus spits out an electron. Yet every time they measured, a piece of the energy was missing, seemingly disappearing into thin air. The numbers refused to add up, threatening a fundamental law of physics, the conservation of energy. It was a crisis. In a desperate move to save this cherished principle, physicist Wolfgang Pauli proposed a radical idea in 1930. He suggested an invisible culprit, a ghost particle that was carrying away the missing energy. He called it a neutron, a name later changed to neutrino, meaning little neutral one. Pauli himself thought it was a desperate remedy, a particle so elusive it might never be found. He even apologized to his colleagues for proposing something that seemed impossible to detect. For decades, the neutrino remained a phantom, a mathematical fix to an embarrassing problem. Then, in 1956, Frederick Riones and Clyde Cowan accidentally stumbled upon proof. They were not even looking for neutrinos directly. They were monitoring a powerful nuclear reactor, knowing its core should be flooded with these hypothetical particles. Their detector, a large tank of water, was designed to catch the incredibly rare moment a neutrino would interact with a proton, producing a tiny, specific flash of light. Against all odds, they saw it. The ghost had been caught. The discovery confirmed the neutrino's bizarre properties. It has no electric charge and almost no mass, so little that for a long time it was thought to be completely massless. It interacts with matter so weakly that trillions of them are streaming through your body every second, from the sun and other cosmic sources, without you ever noticing. They pass through the entire Earth as if it were a ghost. This elusiveness is not a flaw but a feature, pointing to a deeper layer of reality where forces interact with incredible subtlety. The neutrino's existence revealed the weak nuclear force, one of the four fundamental forces of nature, which governs how particles change from one type to another. It showed that what we cannot see directly can be inferred by what is missing, by the gaps in our equations. This principle now guides the search for dark matter, another invisible component of the universe whose presence is felt only through its gravitational pull on galaxies. The story of the neutrino teaches us that reality is filled with silent actors, entities that shape the cosmos while remaining almost entirely hidden from view. What other ghosts are we walking through right now, completely unaware of their presence? Electrons can feel a ghostly presence even when nothing is there. Yakir Aharonov and David Bohm proposed a thought experiment in 1959 that seemed to defy common sense. They pictured a beam of electrons splitting in two, traveling around either side of a perfectly shielded, long solenoid, a cylinder that contains a powerful magnetic field. The crucial detail is this: the magnetic field is completely confined inside the cylinder. The electrons themselves pass only through regions of space where the magnetic field is precisely zero. According to classical physics, the electrons should feel nothing and continue on their way as if the solenoid was not even there. Yet when the two electron beams recombined, their quantum wave patterns were shifted. They had interfered with each other differently, as if something had nudged their rhythm out of sync. The electrons were somehow aware of the hidden magnetic field. This was the Aharonov-Bohm effect, an accidental discovery that proved our understanding of force was incomplete. The secret was not the magnetic field itself, but something more fundamental called the electromagnetic potential. This is a mathematical object that physicists had largely considered a mere convenience, a tool for calculating the real forces. Aharonov and Bohm showed that the potential itself has direct physical reality. Even in a region with zero electric and magnetic fields, the potential can still leave its mark, imprinting a phase shift on the electron's wave function. It is as if you walked through two different corridors that were both completely flat and empty, yet you arrived at the other end out of step with someone who took the other path, simply because the corridors had different hidden histories. This effect reveals a deeper, topological layer to reality. Topology is the study of properties that remain unchanged by stretching or bending, like the number of holes in a donut. The Aharonov-Bohm effect depends not on local details, but on this global, topological property. Is there a magnetic flux trapped inside the region? That single yes or no question, a topological fact, dictates the behavior of the electrons outside, in a region the field never touches. Quantum experts point to this as profound evidence for non-local potentials, where reality is shaped by conditions in places a particle never visits. It challenges our most basic assumptions about locality, suggesting the universe is stitched together by connections that ignore our classical notions of proximity and direct contact. The very geometry of space itself becomes an active player in the drama of physics, a hidden stage director guiding the actors from the wings. How many other invisible scripts are being written in the topological fabric of the cosmos, scripts that dictate the behavior of everything from electrons to light? The grandest motion in the universe was discovered by staring at tiny, blurry smudges of light. Edwin Hubble, working with the most powerful telescope of his era in the 1920s, was meticulously measuring the distances to these smudges, which we now know are other galaxies. He combined his distance measurements with the work of other astronomers who had already observed a strange pattern in the light from these galaxies. Their light was not pristine. It was stretched, shifted toward the red end of the spectrum, a phenomenon known as redshift. Everyone expected these redshifts to be random, a simple consequence of galaxies drifting in a static, unchanging cosmos. Hubble's genius was to compare these redshifts with his own painstaking distance measurements. The correlation he found was not just surprising, it was earth-shattering. The farther away a galaxy was, the greater its redshift, and therefore the faster it was moving away from us. The universe was not static at all. It was flying apart, with every galaxy receding from every other galaxy, as if the entire cosmos were the surface of an inflating balloon. This was the accidental discovery of the expanding universe. The space between galaxies is not empty nothingness. It is an active, stretching fabric. The galaxies themselves are not simply moving through this space. They are being carried along as the very stage of the universe expands. This single observation transformed our cosmic story. It pointed backward in time to a moment of incredible density and heat, a singular beginning we now call the Big Bang. It redefined our place in the cosmos, showing that we live not in a fixed, eternal arena, but within a dynamic, evolving entity with a history and a future. This revelation connected the local behavior of light from a distant nebula to the ultimate fate of everything. Yet this expansion held another, even deeper secret, one that would only reveal itself decades later when astronomers looked even farther into the past. Hubble's expanding universe held a secret about its own future. For decades, cosmologists assumed the mutual gravitational pull of all the galaxies would act like a cosmic brake, gradually slowing the expansion over billions of years. The big question was by how much. In the late 1990s, two independent teams of astronomers set out to measure this deceleration with exquisite precision. Their tool was a specific type of exploding star, a Type 1, a supernova, which always explodes with nearly the same intrinsic brightness. This makes them perfect standard candles. By observing how dim these supernovae appeared in distant galaxies, astronomers could measure vast cosmic distances. By then measuring the redshift of those same galaxies, they could determine how fast the universe was expanding at different points in its past. They were fully prepared to chart the slowdown. The data came in, and it pointed to the exact opposite. The most distant supernova, the ones that exploded when the universe was much younger, were fainter than anyone had predicted. This meant they were farther away than the decelerating model could account for. The expansion of the universe was not slowing down at all. It was speeding up. This was the stunning, accidental discovery of the accelerating universe. The teams, led by Saul Perlmutter and by Brian Schmidt and Adam Rees, had stumbled upon one of the greatest mysteries in all of science. Something was pushing the cosmos apart, a repulsive force overwhelming the pull of gravity. This something was given a name, dark energy. It is not a substance in the normal sense, but a property of space itself, a kind of anti-gravity woven into the fabric of the vacuum. The most shocking part was the scale of this revelation. Measurements now suggest dark energy makes up about 68% of the total energy content of the entire cosmos. The stars, planets, galaxies, and all the atoms we know and are made of account for less than 5%. The rest is dark matter. This means the universe we see is just a tiny fraction of reality, a visible froth on a deep, dark ocean of unknown forces. The discovery of dark energy was a profound paradigm shift. It revealed a deeper structure where the dominant component of reality is not matter, but a mysterious energy that causes space to stretch apart at an ever-increasing rate. This forces a complete rethinking of the universe's ultimate fate. Instead of a big crunch where everything collapses back together, we now face a future of endless, accelerating expansion, where distant galaxies will eventually fade from view entirely. How can it be that the force shaping the long-term destiny of the cosmos is one we cannot see, touch, or yet fully explain? This great cosmic surprise reminds us that our most fundamental theories are still incomplete, and that the deepest layers of reality continue to hide in plain sight. A beam of alpha particles, the heavy, positively charged helium nuclei, streamed toward a sheet of gold foil so thin it was barely there, the prevailing model of the atom, J. Thomson's plum pudding suggested these projectiles would pass through with only the gentlest of deflections. The atom was imagined as a diffuse, positively charged pudding with light, negative electrons embedded within like plums. A speeding alpha particle should slice through this soft cloud, its path barely wavering. The young physicists Hans Geiger and Ernest Marsden, under the direction of Ernest Rutherford, set up their apparatus to confirm this gentle scattering. What they witnessed defied all expectation. While most particles did indeed zip straight through, a few, about 1 in every 8,000, did something extraordinary. They bounced back. It was as if you fired a cannonball at a tissue and it ricocheted straight back at you. Rutherford later expressed his astonishment, saying it was the most incredible event of his life, as if you fired a 15-inch naval shell at a piece of tissue paper and it came back and hit you. This was no slight deflection. This was a complete reversal, a rebound that should have been utterly impossible. That startling rebound was the key to a hidden architecture. Rutherford realized the only way a positively charged alpha particle could be repelled so violently was if the atom's positive charge, and nearly all its mass, was not spread out but concentrated into an incredibly tiny, phenomenally dense core. He called this the nucleus. The calculations were breathtaking. The atom was not a soft pudding, but mostly empty space. If an atom were the size of a football stadium, the nucleus would be a single marble sitting on the 50-yard line, with electrons whizzing around in the distant stands. The solid table in front of you is, at its heart, an immense void, punctuated by unimaginably dense pinpricks of matter. This accidental discovery of the nuclear atom overturned centuries of intuition. It revealed that the forces binding the nucleus must be millions of times stronger than the electromagnetic force that governs chemistry, hinting at the existence of a previously unknown power, the strong nuclear force. This insight does not just explain the atom, it illuminates the cosmos. The same nuclear forces that bind the atom's core also fuel the stars, as the intense pressure and heat in a star's heart force atomic nuclei to fuse together, releasing the energy that lights the universe. How strange that the secret to stellar fire was first glimpsed in a laboratory, in the improbable rebound of a tiny particle from a sliver of gold. The sun's immense power had to come from somewhere, a puzzle that led physicists deep into the heart of nuclear reactions. Hans Bethe, working to pinpoint the source of stellar energy, theorized a process far more elegant than simple hydrogen fusion. He proposed a catalytic cycle where carbon, nitrogen, and oxygen atoms do not get consumed, but instead act as a nuclear machine. In this chain, a carbon-12 nucleus fuses with a hydrogen nucleus, transforming step by step through nitrogen and oxygen isotopes before finally returning to carbon-12 and spitting out a helium nucleus. The carbon is like a cosmic factory foreman, unchanged at the end of the shift, having overseen the transformation of raw hydrogen into precious helium and releasing colossal energy in the process. This was the carbon-nitrogen-oxygen cycle, a hidden engine in stars hotter and more massive than our own sun. Its existence was confirmed indirectly through nuclear physics experiments that recreated these fleeting transitions in particle accelerators, and directly, though unexpectedly, through the detection of neutrinos from the sun. These ghostly particles streaming from the CNO cycle and other fusion processes provided the telltale signature that this intricate dance was real. This discovery revealed a profound truth about the cosmos. The elements are not merely passive ingredients, they are active catalysts in the creation of everything else. The very carbon that makes up life was, and is, a crucial component in the stellar furnaces that forge the elements of reality. This connects the microscopic world of nuclear cross-sections directly to the grand, macroscopic scale of stellar evolution and death. The cycle shows a deeper, recursive structure where the products of earlier cosmic generations become the tools for the next. How many other elemental recipes are written into the fabric of stars, waiting for their conditions to be met? This intricate interplay between the very small and the unimaginably large suggests a universe built on repeating, interconnected patterns, where the same rules govern the atom and the star. Electrons fired like tiny bullets streamed into a chamber filled with mercury vapor. Physicists James Franck and Gustav Hertz expected a simple, continuous process. They thought an electron would collide with a mercury atom and lose a little bit of energy, then a little more in the next collision, its energy draining away in a smooth, gradual slide. Their measurements in 1914 revealed something completely different. The electrons did not lose energy in any random amount. They lost it in sharp, distinct steps, like a ball bouncing down a staircase instead of rolling down a ramp. A specific voltage had to be reached before any energy loss occurred at all, and when it did, it was always the exact same amount. This was an accidental, yet brilliant, confirmation of Niels Bohr's radical new model of the atom. The mercury atoms were not accepting just any energy. They were demanding a precise toll, a specific quantum of energy, to move an electron from one allowed state to another. This was the direct experimental proof of quantized energy levels. An electron orbiting a nucleus cannot exist at any distance it pleases. It is restricted to specific orbits, like rungs on a ladder, and it can only move between them by absorbing or emitting a precise packet of energy. The Franck-Hertz experiment had captured the moment of a quantum jump in action. This granularity is fundamental to the microscopic world. It explains why each chemical element emits and absorbs light only at specific colors, its unique fingerprint. The light from a neon sign is red because the electrons in neon atoms are making jumps between specific energy levels, releasing photons of that exact red color. This discovery peeled back another layer, showing that the stability of matter itself relies on this digital rulebook. Without quantization, electrons would spiral into the nucleus and atoms would instantly collapse. The seemingly smooth world we experience is an emergent property of countless tiny, digital transitions happening all around us. How does this granular atomic architecture then scale up to create the rich, continuous chemistry of life? Absolute zero is the coldest anything can possibly be, a state of complete stillness where all atomic motion ceases. In 1995, physicists Eric Cornell and Carl Wieman aimed for this ultimate chill, using lasers and magnetic fields to cool a cloud of rubidium atoms to within a whisper of that final frontier. They expected the atoms to simply slow down, eventually forming an orderly, frozen crystal. The result was something far stranger. Instead of freezing into a solid, the atoms lost their individual identities entirely. They merged, collapsing into a single, giant quantum entity. This was the accidental creation of a Bose-Einstein condensate, a new and bizarre state of matter. In this super-cold cloud, millions of atoms began to vibrate in perfect unison, their individual wave functions overlapping to become one coherent superatom. You could no longer tell one atom from another. They had become a single collective being described by one shared quantum wave function. For the first time, a purely quantum phenomenon was visible to the naked eye, a tiny cloud in a vacuum chamber that behaved as a single particle on a macroscopic scale. This discovery revealed a profound unity hidden within nature. Under the right conditions, the distinction between individual particles blurs and collective behavior takes over, governed by the strange rules of quantum statistics. It is as if an entire crowd of people suddenly began to move and breathe as one single organism. This coherence hints at a deeper architecture where separateness is an illusion that melts away at ultra-low temperatures. The Bose-Einstein condensate is a direct window into a world where quantum weirdness is not confined to the microscopic. It shows that the potential for unity and coherence is built into the fabric of reality itself, waiting for the right conditions to emerge on a scale we can see and touch. How many other collective phenomena are hiding in plain sight, only visible when we learn to look at the world with a quantum lens? This blurring of the quantum and classical realms suggests that the solid, individual objects we perceive are just one possible state of a much more interconnected and fluid reality. Even the simplest atom held a secret in its fine print. For years, the hydrogen atom was considered a solved problem, its behavior perfectly described by Paul Dirac's elegant equations. Physicist Willis Lamb set out in 1947 to perform a simple task: to measure the energy levels of hydrogen with unprecedented accuracy, expecting his results to confirm Dirac's predictions with a final, satisfying click. Instead, his meticulous measurements detected a tiny, persistent wobble, a subtle energy shift between two specific states that should have been identical according to the theory. This minute discrepancy, known as the Lamb shift, was an experimental accident that cracked open the door to a new era of physics. The perfect vacuum was not so perfect after all. The explanation pointed back to the seething quantum vacuum, that same hidden ocean of energy revealed by the Casimir Effect. An electron orbiting a hydrogen nucleus is not simply a particle circling a point charge. It is constantly buffeted by the fleeting virtual particles popping in and out of existence all around it. These ghostly interactions slightly alter the electron's energy and even blur its position, creating the tiny energy shift that Lamb had so precisely measured. This was the smoking gun, the direct evidence that empty space is alive with activity, and that this activity has measurable consequences for the real world. The Lamb shift demanded a new theoretical framework, one that could account for these wild quantum fluctuations. The result was quantum electrodynamics, or QED, a theory that describes how light and matter interact with breathtaking precision. Physicists like Richard Feynman, Julian Schwinger, and Shinichiro Tominaga developed the mathematical tools to tame the infinities that arose from the vacuum's chaos, showing that these subtle corrections were not errors but essential features of reality. Feynman famously celebrated the agreement between the calculated and measured value of the Lamb shift as a triumph, a moment when human calculation touched the deepest workings of nature. This was more than just fixing a theory. It revealed a cosmos where every particle is in constant, intimate dialogue with the invisible field fluctuations of the void. The solidity of an atom, the very bedrock of chemistry, is an illusion maintained by a delicate balance of these relentless quantum corrections. How many other seemingly settled facts of our world are sustained by such an unseen, turbulent support system? This discovery proved that to see the true structure of reality, we must sometimes look not at the bold strokes, but at the faintest whispers in the data. Deep within a 27-kilometer ring beneath the Swiss-French border, protons race at nearly the speed of light before colliding with unimaginable force. For decades, the grand theory of particle physics, the Standard Model, had a glaring hole. It could explain the forces that govern particles, but it could not explain why those particles had mass at all. The answer was theorized to be a strange and elusive entity, the Higgs boson. Finding it was the primary reason for building the colossal Large Hadron Collider. The search was a monumental effort, sifting through the debris of trillions of collisions, looking for a specific, predicted signal among countless possibilities. Then, in 2012, the data from the massive detectors, a TLS and CMS, converged on a tiny bump, a slight excess of events at a specific energy. This was not a loud announcement, but a quiet statistical whisper emerging from a sea of noise. It was the Higgs boson. This accidental highlight in the data, this subtle anomaly that matched the theoretical predictions, was a discovery that completed a chapter in our understanding of the universe. But the particle itself was not the real story. The Higgs boson is merely the visible sign of something far more profound, a field that permeates all of space, the Higgs field. Think of the entire universe as filled with an invisible, treacly substance. Particles that interact strongly with this field, like the top quark, drag through it and acquire a great deal of mass. Particles that interact weakly, like the photon, zip through entirely unaffected and remain massless. This is the mechanism for mass generation. It was not a property handed to particles at their creation, but an emergent one, granted by their interaction with an omnipresent cosmic field. This process is known as symmetry breaking. In the early, hot universe, all particles were massless and moved at the speed of light. As the cosmos cooled, the Higgs field switched on like a universal freeze, breaking the symmetry of the laws of physics and giving different particles their distinct masses. Without this field, electrons would not be able to form stable atoms, and chemistry and life as we know it would be impossible. The discovery tied together theoretical threads that had been dangling for half a century, revealing a deeper structure where the most fundamental properties of reality, like mass, are not intrinsic but are granted by invisible fields. It completed the Standard Model, yet it also opened a new frontier. The Higgs boson was the last missing piece of the visible puzzle, but its existence encourages a deeper question. What other particles, what other fields are lurking just beyond our current reach, unseen and unfelt, yet shaping the very nature of our reality in ways we have not yet begun to imagine? Gamma rays fired from an atomic nucleus should kick back like a cannon. Every action has an equal and opposite reaction, and the emission of a high-energy photon should send the nucleus recoiling, stealing a tiny bit of the photon's energy and blurring its precise frequency. This was the established expectation when Rudolf Mössbauer began his doctoral work in the late 1950s. He was studying the resonant absorption of gamma rays by atomic nuclei, a process notoriously difficult to observe because of this recoil-induced energy loss. To minimize the effect, he chilled his radioactive source to extremely low temperatures, embedding the atoms in a solid iridium crystal. He expected the recoil to be smaller, but the results were far more dramatic. At a specific frigid temperature, the recoil did not just shrink, it vanished entirely. The gamma rays were being emitted with their full, pristine energy, as if the nucleus had not moved at all. This was the accidental discovery of recoilless nuclear resonance, the Mössbauer effect. The secret was not in the individual nucleus, but in the collective whole of the crystal lattice. In a solid, atoms are not free individuals. They are bound tightly to their neighbors, locked into a rigid, vibrating structure. When a nucleus in this lattice emits a gamma ray, the recoil momentum is not absorbed by that single atom. Instead, it is transferred to the entire crystal. The mass of an entire crystal is so immense compared to a single nucleus that the recoil energy becomes effectively zero. It is like firing a gun while standing on a planet. The bullet leaves with its full energy while the planet does not measurably move. This tiny, recoilless effect opened a door to measurements of almost unimaginable precision. It provided the perfect tool for the Pound-Rybke experiment we discussed earlier, allowing them to measure the gravitational redshift of light with a precision of parts in 1,000 trillion. Without the Mössbauer effect, that test of general relativity would have been impossible, but the implications ran even deeper. The effect revealed a hidden quantum coherence within solid matter. The nuclei in the crystal were not acting alone. They were behaving as a single, entangled quantum system, their collective mass enabling a perfectly sharp, resonant conversation. This coherence is a fragile thing, easily destroyed by heat or disorder, but when conditions are right, it shows that the solid objects around us are not just inanimate lumps. They are vast, coordinated ensembles where quantum rules operate on a grand scale. Physicists quickly realized this was more than a curiosity. It became a powerful spectroscopic tool, a kind of quantum stethoscope. By measuring the tiny shifts in the gamma ray frequency absorbed by different materials, scientists could listen to the subtle whispers of a nucleus's chemical environment. They could probe magnetic fields inside materials, study the nature of chemical bonds, and analyze the composition of rocks from the moon. This accidental discovery demonstrated that reality's apparent stability is not a dull, static thing. It is a precise and delicate condition that, when understood, allows us to perceive the universe with a clarity we never thought possible. The rigid lattice of a crystal, a constraint we take for granted, becomes the very key that unlocks a deeper quantum unity, showing once again that limits can sometimes reveal the most profound freedoms. A material can be a conductor or an insulator, a seemingly straightforward binary choice rooted in a century of physics. Yet in the early 2000s, experiments on certain alloys of bismuth and antimony revealed something that defied this simple classification. These materials, when probed, acted as perfect insulators in their interior, blocking the flow of electricity entirely, but their surfaces told a different story. They conducted electricity with nearly perfect efficiency, as if a thin, invisible skin of metal had been painted onto an insulating block. This was not a surface contamination or a manufacturing defect. It was a fundamental property of a new phase of matter, accidentally discovered while studying materials thought to be well understood. The phenomenon was dubbed the topological insulator. The secret to this bizarre behavior lies not in the chemistry of the atoms, but in the global, geometric arrangement of their electron waves. Physicists recognized this as a topological state. Topology, you might recall, is the branch of mathematics concerned with properties that remain unchanged by continuous deformation, like the single hole in a donut that persists even if you stretch it into a coffee mug. In a topological insulator, the electronic structure of the entire bulk material possesses a specific, hidden topological order. This abstract mathematical property, a kind of twist in the fabric of the material's quantum wave functions, has a direct and unavoidable physical consequence. It forces the existence of perfectly conducting states on its boundary, on its surface. These surface states are not just there, they are protected. They are robust against impurities, defects, and disorder that would normally destroy conductivity in an ordinary metal. It is as if the geometry of the entire object has issued a decree that its surface must conduct, a rule so fundamental that local imperfections cannot repeal it. This discovery revealed a deeper layer of reality where the most practical properties of a substance, like whether it conducts electricity, can emerge not from its local chemistry alone, but from a global, invisible architecture. The implications ripple outward, suggesting a new principle for designing electronics. We could potentially build circuits where the flow of information is protected by mathematical law, inherently resistant to the noise and decay that plague conventional devices. This makes topological insulators a prime candidate for the fragile qubits needed in quantum computing. But the greater revelation is philosophical. It shows that the universe seems to respect these abstract topological rules, weaving them into the very behavior of electrons. If a simple geometric concept can dictate how matter behaves, what other profound realities are waiting to be read from the hidden mathematical script of the cosmos? A delicate torsion balance hung in a quiet laboratory was designed to measure a difference that might not exist. Hungarian physicist Laurent Ertvers meticulously compared two types of mass: gravitational mass, which responds to a planet's pull, and inertial mass, which resists being pushed. He expected that perhaps different materials with their unique atomic structures might reveal a slight discrepancy between these two concepts. His results, refined over years of painstaking work, were unequivocal. The two masses were identical, equivalent to an astonishing precision. He had accidentally confirmed a profound symmetry of nature, one that would become a cornerstone of our deepest theory of gravity. This is the equivalence principle. It states that the effects of gravity are locally indistinguishable from the effects of acceleration. If you were in a windowless elevator car being accelerated through empty space at 9.8 meters per second squared, you would feel a force pinning you to the floor that is completely identical to the force of Earth's gravity. There would be no experiment you could perform inside that box to tell the difference. Ertvers' work revealed that gravity is not a force that acts on objects based on their composition. It is a universal influence on the very stage of reality itself. The reason all objects fall at the same rate in a vacuum, a feather and a hammer landing simultaneously, is because gravity is not pulling them. It is shaping the path they travel along. This principle of equivalence became the engine for Einstein's general relativity. He realized that if you cannot tell gravity apart from acceleration, then gravity must be a manifestation of the geometry of spacetime. A massive object like the Sun warps the spacetime around it, and the Earth simply follows the straightest possible path through that curved geometry, an orbit. Ertvers' meticulous null result, his finding of no difference, was a quiet whisper that pointed toward this roaring truth. The universe treats all mass equally because gravity is not a force in the traditional sense, but the curvature of the cosmic fabric. This profound unity, where the laws of motion and gravity are woven from the same cloth, provides the foundation for our most sensitive investigations into the cosmos today. It is this very principle that allows us to interpret the ripples in spacetime we call gravitational waves, confident that their message of colliding black holes is a universal one, undisturbed by what those cosmic giants are made of. How many other universal symmetries are waiting to be found, dictating the rules of reality from behind a veil of perfect equivalence? For decades, the Laser Interferometer Gravitational Wave Observatory, or LIGO, was a monument to a beautiful theory in search of proof. Its design was a masterpiece of precision with two 4-kilometer-long arms arranged in an L shape. A single laser beam was split, sent racing down each vacuum tube, reflected back by mirrors, and then recombined. The entire system was built to detect a distortion so minuscule it defies belief, a change in length thousands of times smaller than a single proton. The expectation for years was a profound silence, a null result confirming the quiet stillness of spacetime. Then, on September 14, 2015, the silence broke. A signal, a gentle chirp that lasted less than half a second, swept through the detectors in Louisiana and Washington. It was not a random blip. It was the specific waveform, the cosmic fingerprint, of two black holes, each about 30 times the mass of our Sun, spiraling into each other and merging in a cataclysm a billion light-years away. They had accidentally captured the first direct evidence of gravitational waves. The discovery revealed a deeper dynamic structure to the cosmos. Einstein had predicted that massive accelerating objects would create ripples in the fabric of spacetime itself, waves of gravity that travel at the speed of light, stretching and squeezing everything in their path. But to finally witness it was to confirm that spacetime is not a static stage. It is a dynamic, elastic material that can vibrate and ring like a drum. The chirp was that ring, a direct message from the warped geometry of merging black holes. This opened an entirely new window on the universe. For all of human history, we have studied the cosmos through light, from visible rays to radio waves. Now we can listen to it. Gravitational waves are not blocked by cosmic dust or dimmed by distance in the same way. They carry information about the most violent and invisible events, the collisions of neutron stars and the birth of black holes, phenomena that were once only theoretical. Each ripple is a story, a cosmic history written in the language of geometry. How many more stories are traveling toward us right now, encoded in silent tremors that shift the very foundations of reality? This detection connects the most abstract mathematical predictions to tangible, observable phenomena, proving once again that the universe is not just stranger than we imagine, but that it is willing to send us a whisper, if only we build an instrument sensitive enough to hear it. Electrons trapped in a flat, two-dimensional plane should have behaved predictably. When scientists like Klaus von Klitzing applied a strong magnetic field perpendicular to such a sheet of electrons, classical physics suggested the electrical resistance across the material would increase in a smooth, continuous line as the magnetic field grew stronger. The actual results, first clearly measured in 1980, were a complete shock. The resistance did not slide, it jumped. It locked onto specific, precise plateaus, values that were quantized and related to fundamental constants of nature with breathtaking accuracy. This was the accidental discovery of the quantum Hall effect. The resistance was not just any number. It was precisely the resistance quantum divided by an integer, a value so stable and universal, it is now used to define the standard for electrical resistance worldwide. But the deeper mystery was yet to come. Later experiments with purer materials and even stronger magnetic fields revealed something that seemed impossible. The resistance plateaus began to appear at fractional values, not just whole numbers. The electrons, under these extreme conditions, were organizing themselves into a new collective state where the fundamental units of charge were no longer the familiar electron charge, but a fraction of it, like 1/3 or 1/5. This was not a breakdown of physics, it was the emergence of a new physics. The explanation lies in the concept of quasiparticles. In this bizarre two-dimensional electron sea, the intense magnetic field and the interactions between the electrons themselves force the system into a highly ordered, correlated state. The individual electrons lose their identity. In their place, excitations appear that behave like particles carrying a fraction of the electron's charge. These are not actual particles you can bottle up. They are emergent phenomena, collective excitations of the entire electron system that, for all practical purposes, act as if they are new fundamental particles with fractional charge. This discovery peeled back a profound layer of reality. It revealed that complexity can give rise to startling simplicity, and that the properties we assign to fundamental objects like charge can be shared and divided among a crowd. The whole becomes more than the sum of its parts, generating new rules and new entities that did not exist in the isolated components. This points to a cosmos built in layers, where each level of organization has its own unique laws and inhabitants, all emerging from the intricate dance of simpler pieces below. How many other collective beings are we walking alongside, invisible to us because we are only looking at the individual threads and not the tapestry they weave? That faint cosmic whisper from the Big Bang held more than just a uniform tone. As satellites like Planck mapped the cosmic microwave background with ever greater precision, they expected to find a nearly perfect, smooth canvas, the final proof of a uniform beginning. Instead, their maps revealed a subtle tapestry of hot and cold spots, tiny anisotropies imprinted on the sky. These were not flaws in the data. They were cosmic hieroglyphics, a frozen record of the universe's first fleeting moments. These minute temperature variations, mere millionths of a degree, tell a profound story. They are the seeds of all structure, the primordial over densities and under densities that gravity would later sculpt into every galaxy, star, and planet we see today. Without these initial wrinkles, the cosmos would have remained a featureless sea of gas, forever dark and empty. The pattern of these anisotropies is a direct probe of the universe's infancy, a baby picture that encodes its composition, shape, and ultimate fate. The specific statistics of these spots, their size and distribution, provide the strongest evidence for cosmic inflation, the theory that the universe underwent an unimaginably rapid exponential expansion in the first fraction of a second. This inflationary burst would have stretched quantum fluctuations, those tiny jitters from the subatomic world, to cosmological sizes, planting the seeds for everything to come. This is the stunning connection, where the microscopic quantum realm directly dictates the macroscopic architecture of the cosmos. The very largest structures we observe, the great walls and voids of the cosmic web, were born from the tiniest possible quantum vibrations, magnified across the entire universe. Furthermore, the detailed properties of these anisotropies offer crucial clues about dark energy, the mysterious force driving the universe's accelerated expansion. The way these spots are subtly distorted reveals how dark energy has influenced the growth of cosmic structures over billions of years. How can it be that the entire grand narrative of the universe, from the first instant to the present day, is written in the faint temperature differences of its oldest light? This discovery forces us to see reality as a single, continuous whole, where the quantum and the cosmic are inextricably linked, and the initial conditions of creation are forever etched into the fabric of the sky. A star's core is a place of immense pressure and heat, where atomic nuclei race toward each other at tremendous speeds. Yet, even with this energy, a fundamental problem remains. Every nucleus carries a positive charge, and similar charges violently repel one another. The electrical force creating this barrier is colossal. By all classical rights, most nuclei in the Sun should not have enough energy to overcome this repulsion and get close enough to fuse. They should simply bounce off like two powerful magnets pressed together at the wrong ends. The fact that stars shine at all was for a time a deep mystery. The answer arrived through an accidental discovery in both astrophysics and laboratory experiments. revealing a loophole in the laws of physics. Particles with seemingly insufficient energy were somehow fusing. They were not going over the energy barrier, they were going through it. This is the phenomenon of quantum tunneling. At the quantum scale, particles are not just tiny billiard balls. They are also waves of probability, described by a wave function that does not abruptly end at a barrier's edge. Instead, it decays exponentially, but it never quite reaches zero. There is a small but non-zero probability that the particle will simply appear on the other side of the barrier, as if it dug a tunnel straight through an impassable mountain. This is not science fiction. It is a fundamental feature of our reality, one that makes our universe possible. Without quantum tunneling, the nuclear fusion that powers stars would fizzle out. The Sun and all other stars would be dark. The probability for any single proton to tunnel into another is incredibly low, but the sheer number of collisions in a stellar core makes this rare event occur constantly, providing the steady, life-giving energy that has shone for billions of years. This deeper probabilistic structure transforms impossibility into a matter of chance. The same principle has been harnessed here on Earth in remarkable technologies. The scanning tunneling microscope does not use a lens to see atoms. It uses a needle so fine its tip is a single atom. It is brought excruciatingly close to a surface, but without touching. Electrons then quantum tunnel across the gap between the tip and the sample. By measuring this tunneling current, the instrument can map the contours of individual atoms, rendering the invisible world visible for the first time. This entire field of nanotechnology rests on this quantum loophole. How can a rule so strange and counterintuitive be the very reason for light and life? Quantum tunneling demonstrates that the universe is not built on certainties, but on probabilities and potentialities. It shows that barriers we perceive as absolute are, in fact, permeable. The solid walls of classical physics are, at the quantum level, merely translucent veils. This final accidental discovery, like the 26 that came before it, peels back another layer, revealing a cosmos where the impossible is merely improbable, and where the deepest structures are woven from chance and connection. These 27 accidents form a constellation, a scattered map of a hidden continent. Each discovery, from the quantum jitters in an atom to the silent pull of dark energy, is not an isolated island of knowledge. They are all connected, points of light revealing a single, breathtaking structure of reality. We have been charting this territory piece by piece, but the true revelation is the landscape itself. It is a cosmos built in layers, where the familiar world of solid objects and definite locations is an emergent illusion, a surface phenomenon resting upon deeper, more fundamental strata. At the base lies the quantum field, a seething, probabilistic foundation where particles are mere excitations, and the void is alive with potential. This gives rise to a granular, quantized world where properties like energy and spin come in discrete packets, not smooth flows. These quantum rules then scale upward, governed by profound symmetries and their breaking, to create the forces and particles that build our atoms. This entire intricate dance is set upon the dynamic stage of spacetime, a flexible fabric that curves, ripples, and expands, weaving matter and geometry into an inseparable whole. The themes echo from the smallest scale to the largest, non-locality, revealed in the spooky connection of entangled particles, tells us that separateness is an illusion. The universe is profoundly interconnected, a holistic web where distance is no barrier to relationship. Quantization, from the Stern-Gerlach experiment to the quantum Hall effect, shows us that reality is digital at its core, built from finite, precise steps. And symmetry breaking, elegantly confirmed by the Higgs boson. demonstrates how the rich diversity of our world, from the variety of particles to the very existence of mass, emerged from a more perfect, symmetric beginning as the cosmos cooled. Thinkers like Carlo Rovelli suggest that the properties of things only exist in relation to other things. An electron has no definite position until it interacts, until it relates to something else in the universe. This relational view dissolves the idea of a static, background reality. Lee Smollen's temporal naturalism takes this further, proposing that even the laws of physics may not be eternal, but could evolve in time, a universe learning its own rules as it unfolds. This grand synthesis paints a picture of a reality that is not a fixed, pre-written script, but a dynamic, ongoing process. It is a fabric of relationships, a network of events where the whole is constantly giving rise to the parts, and the parts, in turn, define the whole. Our journey through these accidental discoveries shows that our understanding of this structure does not progress in a straight line. It lurches forward through surprises, through the stubborn glitches that refuse to be ignored. The deepest truths of the cosmos are not found by staring directly at them, but are glimpsed from the corner of our eye, in the patterns of what goes wonderfully, illuminatingly wrong. This perspective transforms our place within it all. We are not passive observers of a finished cosmos. We are active participants in a reality that is still unfolding, a dynamic fabric that we are only just beginning to learn how to read. These 27 accidents form a constellation, a scattered map of a hidden continent. Each discovery, from the quantum jitters in an atom to the silent pull of dark energy, is not an isolated island of knowledge. They are all connected, points of light revealing a single, breathtaking structure of reality. We have been charting this territory piece by piece, but the true revelation is the landscape itself. It is a cosmos built in layers, where the familiar world of solid objects and definite locations is an emergent illusion, a surface phenomenon resting upon deeper, more fundamental strata. At the base lies the quantum field, a seething, probabilistic foundation where particles are mere excitations, and the void is alive with potential. This gives rise to a granular, quantized world where properties like energy and spin come in discrete packets, not smooth flows. These quantum rules then scale upward, governed by profound symmetries and their breaking, to create the forces and particles that build our atoms. This entire intricate dance is set upon the dynamic stage of spacetime, a flexible fabric that curves, ripples, and expands, weaving matter and geometry into an inseparable whole. The themes echo from the smallest scale to the largest, non-locality, revealed in the spooky connection of entangled particles, tells us that separateness is an illusion. The universe is profoundly interconnected, a holistic web where distance is no barrier to relationship. Quantization, from the Stern-Gerlach experiment to the quantum Hall effect, shows us that reality is digital at its core, built from finite, precise steps. And symmetry breaking, elegantly confirmed by the Higgs boson, demonstrates how the rich diversity of our world, from the variety of particles to the very existence of mass, emerged from a more perfect, symmetric beginning as the cosmos cooled. Thinkers like Carlo Rovelli suggest that the properties of things only exist in relation to other things. An electron has no definite position until it interacts, until it relates to something else in the universe. This relational view dissolves the idea of a static, background reality. Lee Smollen's temporal naturalism takes this further, proposing that even the laws of physics may not be eternal, but could evolve in time, a universe learning its own rules as it unfolds. This grand synthesis paints a picture of a reality that is not a fixed, pre-written script, but a dynamic, ongoing process. It is a fabric of relationships, a network of events where the whole is constantly giving rise to the parts, and the parts in turn define the whole. Our journey through these accidental discoveries shows that our understanding of this structure does not progress in a straight line. It lurches forward through surprises, through the stubborn glitches that refuse to be ignored. The deepest truths of the cosmos are not found by staring directly at them, but are glimpsed from the corner of our eye, in the patterns of what goes wonderfully, illuminatingly wrong. This perspective transforms our place within it all. We are not passive observers of a finished cosmos. We are active participants in a reality that is still unfolding, a dynamic fabric that we are only just beginning to learn how to read. The physicist Richard Feynman captured this beautifully when he said, "Nature uses only the longest threads to weave her patterns, so each small piece of her fabric reveals the organization of the entire tapestry." Every one of these 27 experiments, from a fogged photographic plate to a faint gravitational chirp, is one of those small pieces. Each one, no matter how accidental, pulls on a thread that connects to the whole grand design. This is the ultimate lesson. Stay curious, pay attention to the outliers and the mysteries. Which of these unplanned revelations surprised you the most? Let us know your thoughts in the comments below, and if this journey into the hidden architecture of reality has sparked your wonder, subscribe for more explorations into the deepest mysteries of space. The universe is whispering its secrets. All we have to do is learn how